Hello, and welcome to the video series on the Tour of Go exercise walkthroughs. Today's video covers the 10th exercise, equivalent binary trees, from the concurrency module inside of the concurrency chapter. Rather than just showing you my solution directly, I will explain all the necessary goal-line concepts in context for you to impart with a deep understanding of what each and every single line of code really means. The exercise description is longer than usual and spans 2 pages. On the first page, we get a high-level overview of what we'll be doing. And on the second page, we see step-by-step instructions as well as the code editor. So what is this question asking of us? At a high level, we'll implement a concurrent algorithm to check whether two binary trees have the same sequence of values. The crucial idea is that we compare the values, but the shapes of the two trees can be completely different. The binary tree implementation is already provided via a custom package. It's a symbol struct with 3 fields: left, value, and right. Left and right are pointers to trees, and value is an int. So a tree points to its left and right subtrees, which in turn also point to its subtrees. And at the bottom of the tree, left and right will just be set to nil. Okay, moving on to the second page. Here we have the detailed steps, but essentially we need to implement 2 functions. First, the walk function, which implements an in-order traversal from the leftmost node to the rightmost node. And second, the same function, which uses walk to check if 2 trees have the same values. We'll refer back to these steps as we implement the solution together, but let's first have a look at the starter code. The function signatures for the 2 functions are provided for us. Same determines whether the trees t1 and t2 contain the same values. t1 and t2 are of type pointer to tree, and the function returns a bool. Same will make use of the walk function, which walks the tree t, sending all values from the tree to the channel. A channel is basically a typed conduit, allowing us to send and receive values between goroutines. And a goroutine is simply a lightweight thread managed by the Go runtime. Tying this back to our exercise, same will kick off 2 goroutines to walk t1 and t2 concurrently. And as each walk processes the values in its tree, it sends them back over a channel so that same can compare the sequences. This will all make sense once we get coding. Besides the function signatures, we have an empty main function, and the tree package is already imported. Let's check out its docs. Again, we have the tree struct we saw earlier. There's also a function new, which returns a new random binary tree holding the values k, 2k, up to 10k. Lastly, there's a string method, which makes tree conform to func.stringer, which means we can print out trees directly using func.println, for example. Cool. So let's create some trees to set up our implementation. The 2 functions are missing a function body, so we'll give them a minimal implementation. There we go. The trees aren't printed in the most beautiful format, but the key thing to notice is that they hold the same sequence of values while having different shapes. Running the same code again regenerates both trees with different shapes. Now let's implement walk and test it by printing out the first 10 values of t1 by reading from its channel. First, we'll create the channel. When creating channels, we need to use the built-in make function, as we do for slices and maps. Then we'll call walk. To make walk run as a goroutine, we just add the keyword go in front of the function call. As walk now concurrently processes the tree, it will be sending values to the channel. And here in main, we'll be receiving those values and print them out. For range 10 means that the body of the loop will execute 10 times. Inside of the loop, this statement means wait until there is a value that can be received from the channel, and once it is available, consume it and store it in V. Then we just print out V. That's all for the caller side of walk. Now let's move on to the actual function implementation. We'll implement walk as a recursive function, calling itself with the left and right subtrees of t until there are no more children. This means that walk will eventually be called with a nil tree, which becomes the base case of our recursion. If we're at a non-nil node, we first call walk on the left subtree. Then we send the value on the channel. And finally, we call walk on the right subtree. That's the entire walk implementation. Let's run. And it works as expected. However, our code only works cleanly when the tree has exactly 10 nodes. What if we change that assumption and expect the tree to have less than 10 nodes? The program exits normally, but the walk goroutine just gets cleaned up automatically by the runtime as the main function finishes. That's not too bad, but what if we assume the function has more than 10 values? Now the program runs into a deadlock. At the 11th iteration of the loop, we wait to receive a new value from the channel, but walk has already finished, and there are no other goroutines that could potentially send to that channel. So the runtime correctly detects that, yeah, all goroutines are asleep and we're at a deadlock. Wouldn't it be nice if we could receive the exact number of values that are sent to the channel? Even better, what if we could just range over the channel like we do for a slice or an array? This construct is actually valid. All we need to do for this to work is to signal that no further values will be sent to the channel. Go provides the built-in close function that does exactly that. So coming back to our walk function here, we need to make sure that all values are sent before we close the channel. To do this, we'll move our current recursive walk logic into a separate helper function. The recursive implementation is now the unexported walk helper, and the exported walk function simply calls it. This allows us to then close the channel. Now we no longer hardcode the exact number of tree values. First, let's see how we'll call same from our main function. For these two trees, where the sequence of values is the same, we would like to have our same function return true. As I mentioned before, the idea for same is to kick off two goroutines, one to walk T1 and the other to walk T2, each sending values back to same via a channel. For the first iteration of same, let's again make the simplifying assumption that each tree has exactly 10 values. At each iteration of the loop, we wait to receive one value from each channel. If the values differ, we immediately return false. After 10 iterations without seeing a mismatch, we know the two trees have the same sequence. So for these two trees, the function now correctly returns true. And if we change one of the sequences of values, it correctly returns false. Now let's make same work for trees of any length. Walk already closes the channel once it has sent all the values. So instead of iterating 10 times, we can iterate until one of the channels closes. When we receive from a channel, we can optionally specify a second value that tells us whether the channel is open. Now we'll check if one of the channels has been closed. Okay, let's think about why this works. If both channels are open, we compare V1 and V2 as we did before and return false if they differ. If both channels close at the same time, we've compared all the values successfully and the expression will return true or evaluate to true as false equals false. If one channel closes while the other is still open, then we also hit this if statement and we will return false. The expression evaluates to false. And this makes sense, as one channel closing while the other is still being open means one tree has more nodes to be processed than the other. Great, our implementation is almost perfect. I'd just like to show one more thing. When we specify the type of channel, we can also say whether it's send only or receive only. Adding the arrow after the chan keyword makes the parameter send only. The program still works, but any attempt to receive now from the channel inside of the toWalk functions would cause a compile time error. So if we move the arrow instead in front of chan, this makes the parameter receive only. And now the compiler complains that we cannot send to a receive-only channel, and we cannot close a receive-only channel. Only the sender is allowed to do that. So let's change the arrows back. Great. With that, I just wanted to show how adding channel directions can help us catch concurrency bugs by leveraging the type system. If you've made it this far, thank you so much for watching. We only have one more exercise to work on. Hopefully, I'll see you there. Peace.